السلام عليكم ورحمة الله. الحمد لله والصلاة والسلام على رسول الله صلى الله عليه وسلم. Inshallah, today we are going to start another topic of the states of matter. We spent the last lecture talking about the ideal gases and real gases. And today, inshallah, the lecture is dedicated to start talking about the liquid state. And hopefully by the end of the lecture, we will also talk about the solid state. Okay? So I wish today we can finish states of matter and the properties of liquids and solids as well. But before I proceed, I want to stop a little bit with the last example I gave you in the last lecture for the real gas, because this is very important also, and I wish to recognize and appreciate the contributions of the volume corrections and the attraction corrections for the general gas law. As I mentioned in the last lecture, we have two things we need to correct for the behavior of ideal gas to imitate the real case of gases. You remember? The ideal behavior ignored the volume of the gases. And in the correction, what did I do in the correction for the volume correction? I subtracted the internal volume or the particles volume of the gases itself, right? And instead of considering the volume of the container, which is V, I did the correction to be the real volume as V minus NP, right? Where N is the number of moles of the gas, B is the molar volume of the gas. Molar volume, which is the volume of 1 mole of the gas, right? Okay, I'm just refreshing the information I gave last lecture. Okay, this is for the volume correction, and for the pressure correction or for the attraction forces, I subtracted a value of A times N over V square, right? This is the internal pressure of the gas, internal pressure. I subtracted the internal pressure of the gas, which originates from the attraction forces between the gas particles, right? Right? Okay, so I will see this in the next example. The example says that using the van der Waals equation is the real gas equation. It's the real gas equation, okay? Calculate the pressure exerted by 1 mole of argon gas in a 22.4 liter container at 273 Kelvin. What do you think about these conditions? This is the STB conditions. Is it the STB condition? STB means we are at 1 atmosphere and 273 Kelvin. By the way, maybe in the last lecture in the recording, you may hear that STB is 273 Kelvin. This is not correct. This is wrong. I misstated the temperature, but STB, as I mentioned in the words itself, STB is the standard temperature and the pressure. This is 1 atmosphere and 0 Celsius, which is 273 Kelvin, okay? So this is, we are now here at the standard temperature, okay? And 1 mole, and as you look here, 1 mole of argon occupy 22.4 liter. And this is the statement we took last lecture, that every single mole at STB occupy 22.4 liter. Okay, so the gas occupies this volume only at STB. So the missing pressure, if you are calculating the ideal pressure, is supposed to be 1 atmosphere under this condition. Even if you apply BV equal to nRT, you apply with these conditions, you have the number of moles, you have the volume of the gas, you have the temperature. Which is missing? The pressure. You already have the R, the universal gas constant. You apply in the equation, you can calculate very simply the pressure. The pressure will be 1 atmosphere. This is ideal behavior. This is ideal behavior. But he is not asking about the ideal behavior. He's not asking about the ideal pressure. Look what he asks. How much is the pressure deviation? Deviation from ideal behavior. Deviation. So you are supposed first to calculate the ideal pressure, and then you calculate the real pressure, and you calculate the difference, the deviation. Okay? So it's asking now to calculate both of them, the ideal and the real. Okay? How can you calculate the real pressure? You apply in the van der Waals equation. So what do you need to calculate the pressure in van der Waals equation? You need the constant. Okay? The A constant, which is located in the pressure correction. Okay? I said that the pressure correction is A times N over V. You have N over V squared, right? You already have N, because it said here 1 mole of gas. You also have V, right? So everything is known. The missing parameter is A. He gave you the A constant. But look at the unit of A constant. It's very important. I want you to look at everything and get the meaning, get the feeling. Okay? Because the pressure correction is basically, as a whole, is a pressure term, right? Is a pressure term, because I said B observed equal to this plus or minus A N over V squared. So the unit of A times N over V squared, what is the unit of this term as a whole? The unit is a pressure, because I subtracted from the pressure. So when you subtract something or add something, it should have the same unit, right? Should have the same unit. So as a whole, the term is a pressure. A times N over V squared equal to pressure unit, right? So how about A itself? So you need to move N over V squared to the other side. So the unit will be liter squared per dot at per mole squared. Okay? This is the opposite unit of N over V squared. Okay? With the pressure included here. Okay? Because if you multiply the unit of A here with the unit of N over V squared, this is supposed to be a pressure term. A pressure term. Okay? And also it gives you B, which is the molar volume. Look at the unit. This is volume per mole. This is the molar volume. So in van der Waals equation, look at van der Waals. As I told you the last time, you need to memorize the equation and to know where the sign is located and to understand the physical meaning of the equation. Okay? What is the physical meaning of the equation? I will tell you now. Okay? Look at this term. This is the volume correction, right? The volume correction. NB is the volume correction. I subtracted this value from the V. What is the impact of subtracting this value from V? What is the impact on the pressure? What do you think? This will increase the pressure or decrease the pressure? What do you think? Will it increase the pressure or decrease the... This is the meaning, okay? Increase or mean? Or increase or decrease? So, if you subtract some value from V, this means that this value will get lowered. If this is lowered, then the pressure will be increased higher, right? So, considering the volume correction in van der Waals equation is supposed to increase the pressure. It's supposed to... do not forget this, because we will play in this area, okay? So the volume correction is supposed to increase the volume, the pressure. It's supposed to increase the pressure. Okay. So if I give you two different gases like neon, which is 1020, okay, and argon, which is 1836. Two different gases. Which is bigger? Neon or argon? Which is bigger? Which is bigger in volume? Which is bigger in size? Which is larger in size? Neon or argon? You should have an idea about the periodic table. You remember this from the first semester, okay? So as you go down in the group, the size increase, right? Or I'm talking something wrong. Okay, as you go down the group, the size increase. So which is larger in size, neon or argon? Argon. One word. I should not attract your attention in the exam for this tricky point. You should know it yourself. If I told you compare between this and that, you go back to the periodic table and see which is above, which is down, which is located. Are they in the same series? Are they in the same group? Which is supposed to be larger? Which is supposed to be is to have the larger attraction forces. You should recognize this and you should understand this. Okay, which is larger, neon or argon? Argon. Which is supposed to have the larger molar size, neon or argon? Also argon. Okay, which is supposed to induct a greater effect for the pressure? The one that has the larger size. Because here, as you compare, we need to consider the molar volume of the gas. Molar volume. Which has the largest molar volume? The one that has the bigger size, right? Argon. So if I asked you which is supposed to deviate more from the volume correction perspective, neon or argon, you should say which one? Argon will deviate more. Argon will deviate more, right? Why? Because it is larger in size. Larger in size, this P will be larger. As it is larger, the volume will decrease larger. Okay? So the pressure will increase. Increase or decrease? Increase. So the correction impacts an increase in the observed pressure. The volume correction inspire an increase in the observed pressure, right? Now we are ignoring the attraction forces. We are ignoring the attraction forces because I should consider it as well with the volume correction. Look at the impact of the attraction forces. Does it increase or decrease the pressure? Increase or decrease? Look at here.
When the volume.
No. I'm saying here, this is the attraction forces as a whole. A times N over V squared. This is the correction for the pressure as a whole. Does it increase B or decrease B? Increase or decrease? Increase? How is increase? Do you see this minus sign? As this pressure increase more, which means more attraction forces, as the attraction forces increase, which that indicates that the pressure will decrease, right? And I described this in the model in the last lecture. As I said, you have one molecule is trying to go to hit the wall of the container. If the attraction forces is more, then it will repel this attraction. Okay, so the pressure will decrease. The pressure will decrease. So as the attraction forces between the particles, the gas particles increase, the pressure will decrease. The observed pressure will, and this is very obvious from the equation. Here we are subtracting this part from nRT over Vn minus Np. So as the internal pressure of the gas increase, the observed pressure will decrease. So we have two different factors now. One is increasing the pressure, which is the volume correction. The other one is decreasing the pressure. So you have to estimate which is influencing more. Which is influencing more. You may, in some circumstances, you may find the contribution of the volume is exactly the same as the contribution of the pressure. In that sense, the real pressure will equal to the ideal pressure, right? So some part will increase the pressure and the other part will decrease the pressure. So finally, you may find the ideal pressure, the real pressure is exactly the same as ideal pressure. In some other cases, you may find the contribution of the pressure is very minor. It's very minor. So we will focus intensively on the volume correction. And maybe the opposite is true, right? So you should consider both terms. So in our example, we are talking about argon. What do you think about the attraction forces in argon? Attraction forces in argon is a noble gas. Argon is a noble gas, and we will discuss after some slides here the different types of attraction forces. Okay, so we will learn that the attraction forces in noble gas is the weakest. It's the weakest. Okay, so the attraction force is very weak in the noble gases. Okay, so I expect from the beginning that the attraction forces will not influence much the observed pressure. But what do you expect? Which will influence the observed pressure? The volume of the argon. The volume will influence the observed pressure much more than the attraction forces. Okay, so this is an expectation from the beginning. Okay, look at this here. If you apply in the pressure, observed pressure, so this is the term of the nRT over V minus NB. This is the term, and this is the other term here. Okay, so finally you will find the pressure equal to 1.1674 minus 0.002. How about this term? This term is very small, right? This is a pressure correction. This is the pressure, this term, A times N over V squared. This is the term. Even if you subtract this value from 1.1674, you will find that the result is exactly very close to the value before the pressure correction, right? So how can you resonate? How can you understand this result? This result, we can understand it in view of the weak attraction forces of argon. The weak attraction forces of argon. So what principally deviated this value from the ideal behavior, which is 1 atmosphere? As I said, the ideal value of the pressure is supposed to be 1 atmosphere, but now in the real is 1.1674. So what principally deviated the ideal, the pressure from the ideal value? Is it the pressure correction or the volume correction? Which one? Which one?
Volume.
Is the volume correction. Okay, so here the main reason for the deviation is the volume correction. Okay, so that's all what I want to explain. Yes.
B minus and B.
Yes.
And
B.
and B.
MB. This is the volume of the particle, total volume of the particle together. N is the number of moles and B is the molar volume. So if you multiply both of them together, so you end up with the volume of the gas, the volume of the gas particles. Okay. Okay. So that's all what we want to describe from the last lecture. Okay. And now I move to the topic of the lecture today, which is principally talking about liquids and solids. Moving from the gas to the liquids and solids, now we should appreciate the attraction forces between particles, right? You know, in contrast to the case of the gases, as I said, the attraction forces are very weak, and the distance between the gas particles are huge, right? But now we are going to the liquid state, so attraction forces is appreciated, and also the distance between the particles will be much less than the gas case. Okay, so before we proceed, you should appreciate the terming of the transformation, states transformation or states conversion. Okay, so as I said, from the solid to the liquid, this is melting, and the opposite is freezing. Okay, and from liquid to gas is evaporation, and the opposite is condensation. And from solid to the gas is condensation, is sublimation. The opposite is deposition. All these transformations are physical in nature. What do I mean by physical in nature? So we do not have any chemical transformation. What does it mean also? So if you have ice, this is a solid state of water, right? What is the composition of ice? Is H2O, right? So when ice converts to liquid water, what is the composition of liquid water? H2O. When water evaporates, what is the composition of vapor, water vapor? Is also H2O, right? So all this, what happened? We are breaking the bonds between the water molecules, not inside the water molecules. Okay, water molecules remain the same, water, H2O, but we are breaking the bonds between water molecules to convert between. It says this is a physical process. A physical process. The bonds between the particles, or the attraction forces between the particles together, is called intermolecular attraction force, or intermolecular force, intermolecular force, intermolecular force, or intermolecular force, right? Okay? But inside the water molecule itself, inside the water molecule, as you know, water molecule, what is the kind of bond in the water molecule between oxygen and hydrogen? Between oxygen and hydrogen. This is a covalent bond. This is covalent bond. The bonds that is existing inside the molecule itself is called intramolecular force. Okay, the forces inside the molecule itself is intramolecular force. So we should differentiate between two different types of forces in the molecules and among the molecules. In the molecules it's called intramolecular force, but among the molecules it's called intermolecular force. What do you think? Which needs more energy to be to break the bonds? Which requires more energy, the inter or the intra? The intra, of course, right? So usually you see a statement that it is easier to evaporate water than to split water. Is this true or wrong? It's true, because to evaporate water, you need to break the bonds between water molecules. This is intermolecular force. Okay, it's easy to do it, but to split water into hydrogen and oxygen, you require more energy, more energy, because you are trying to break intramolecular force, which is chemical bond. This is chemical bond. Now you are converted from the physical state or physical change to a chemical change. You are splitting the molecule. It will not become water anymore, right? If you split H2O, it will not become water, okay? Will be hydrogen and oxygen. So this is a chemical transformation. This is a chemical transformation, okay? So properties of liquid are intermediate between those of solids and the gas. And we learned about this in the last lecture. So the difference between intermolecular and intermolecular forces are those between molecules in the condensed states, like liquids and solids, okay? Even if you consider the bonds between gases also, it can be intermolecular force if you are considering the real case. Between gases particles, this is also intermolecular force. This is always physical in nature, is responsible for the bulk properties of material, like the melting point. If I asked you anything about the physical properties of the liquids, you should definitely connect this to the intermolecular forces between particles, not inside the particles, okay? The other type is intramolecular forces, which hold atoms together within a molecule, which is chemical in nature. And this is an obvious example in the molecule of HCl. Between H and Cl, we have a chemical bond, okay, which is a covalent bond, as I said in the last lecture. In HCl, the bond is covalent, okay? So the forces between H and Cl is basically intramolecular forces. But between HCl and the other molecule of HCl, the force is intermolecular force. And this is the bond which is responsible for the physical changes in the liquid or physical transformation, okay? So intermolecular forces are much weaker than intramolecular forces. So it requires much less energy to evaporate a liquid than to break the bonds in the molecule. Intramolecular forces, we have three different types of intramolecular forces. We will get an overview for every type very quickly, but I'm sure you're already familiar with this type of bonding. Okay, the ionic bonding and the covalent bonding and the metallic. So the electrostatic bonding or the ionic bonding. So in the ionic bonding, one atom gives one or more electrons to the another atom or a group of atoms to achieve the octet rule. Every single atom wants to have in the outer shell level 8 electrons to attain a stable state. So this is the driving force for the ionic bonding. And actually, after attaining this octet rule in the ionic bond, we have a complete donation for the electron. So one atom donates one electron, and the other one accepts the electron. So one atom will become the donating one. The donating one will have a positive charge, and the accepting one will become a negative charge. So basically, we will have a Coulombic attraction between them. Okay. So the nature of the bond is electrostatic, and the driving force is the attraction between the opposite charge. Okay, so we can apply, of course, the Coulomb law for the attraction forces, and as you see here, that the attraction forces is proportional to the charges, the values of the charges. Okay, the multiplication of the charge, and is inversely proportional to the distance between these point charges. Okay, epsilon node here in the equation is the vacuum permittivity. Okay. Okay, the ionic bonds are long-ranged. What does it mean by long-ranged? Long-ranged means that they attract or repel other ions beyond the nearest and the next neighbors. not only the atoms in the nearest neighbor it can interact with, but these attractions can extend to multiple layers. So this is the meaning of long range. It has an impact for long range, the ionic attractions, not only in the same, not only the next one, but maybe the one after the next one, and the one next also, okay? So it has a long range impact. This is the ionic attraction. And it also non-directional. It doesn't require a specific orientation or specific direction. It interacts with everything around, okay? It doesn't need a specific direction, like the covalent bond. We will see this in the covalent bond. If you are not in the proper position, you will not feel the bonding, okay? No, the ionic bond is different. It is non-directional, and it's so strong, somehow around 400 kilojoule per mole, okay? The ionic solids, while stacking atoms, there are no directional requirement, okay? There are no directional requirement. Bonding can be at any angle, but there are a size and the charge requirement. It needs only the size. When you're stacking atoms together, every lattice point will have a specific size. So an atom with the appropriate size should locate in the nearest neighbor, in the nearest neighbor position, okay? It also should have a charge requirement, because positive ion requires a negative ion, okay? And so on. So it needs a size, specific size, and specific charge to be located around it, okay? How about the covalent bond? The covalent bond is based on the sharing of electrons between two different atoms. Sharing of electrons, not donation, okay? Is basically sharing. One pair of electrons, or two pairs of electrons, or three pairs of, and based on that, we will have a single bond, a double bond, and a triple bond, okay? So, and the sharing may originate from both atoms that participate in the bond, or maybe originate from a single atom. The bonding electrons may come from both atoms, or may come from a single atom, okay? If they come from the single atom, we'll call this bond as a coordination bond, covalent bond, okay? So example for this is the bonding in hydrogen molecule, nitrogen, oxygen, chlorine, CH4, okay? And the octet rule is the driving force for this. Yes? Is attraction? Yes, of course. The attraction force between the atoms. Yes, of course. We will see now that the polar, the covalent bond may be polar or non-polar. Even if it is non-polar, okay, they should locate the sharing electrons in between for both to attain the octet rule. So this process will locate both atoms binding together, okay? So the pair of electrons should move around both atoms, okay? So it looks like this is the binder, the pair of electrons, okay? So the covalent bond, the driving force is attaining, as with the octet electronics instruction. Covalent bonds are very short-ranged, in contrast to the ionic bond. It operates in very small distance. It doesn't have a long effect, okay? It is also highly directional and strong, It requires a specific structuring for the covalent bond. So if you look to the methane molecule, the hydrogen atoms should locate in a tetrahedral structure, okay? If you look to other molecules, based on the existence of lone pair of electrons or through covalent bonds, the structure can be assigned. Okay, so it requires a specific orientation. Okay, and if the atom did not satisfy this requirement, it will not form a bond. It will not form a bond. Okay. No charge requirements for the covalent bond. So you can build the crystal with similar charges. Okay, same charge, no problem, is not required in the covalent bond. The covalent bond is strong in the range which extend to 1,000 kilojoule per mole. Of course, sometimes it might be weaker than the ionic bond, but it extends to a high range of bond energy. Okay. As I said, it can be single, double, or triple bond based on the number of sharing electrons. If both shared electrons in a covalent bond come from the same atom, then the bond is called coordinate covalent bond. Covalent bond can be polar or non-polar based on the difference of the electronegativity of the participating atoms. If you look to HCl, we have a large difference in the electronegativity between hydrogen and the chlorine. So we have shared electrons, but chlorine actually attract the shared pair of electrons to it because it has a much higher electronegativity. This will inspire a partial negative charge on the chlorine atoms. In the opposite case, in the other case, the hydrogen will have a partial positive charge. So the overall, the molecule will look like a permanent dipole, which has a positive end and a negative end. Looks like a permanent dipole, okay? And the molecule is said to be a polar molecule, and the bond is said to be polar covalent bond. This is different from the case of hydrogen molecule. Hydrogen molecules, the covalent bond is formed between two similar atoms, or even in chlorine, Cl2. In any bimolecular molecules of the same atom, the bond between the atoms is non-polar. There's no preference for any atom to attract the shared electrons more than the other one, so that the bond is non-polar. So covalent bond can be classified as polar bond or non-polar bond. Okay. The other category of the chemical bond is the metallic bond, and in that point, you know, in the metals we have free electrons in the valence shell, and the free electrons are not localized for the specific atoms they come from. Okay, but they move freely in the crystal lattice, and this is the origin of the this is the reason for the very high electrical and thermal conductivity of metals, and this is the origin also for the malleability and ductility of metals. Okay, so this is called the electron C model. The electrons here, which is supposed to be located at the gold atom, is not located exactly on the gold, but it moves freely to connect the several atoms in the crystal lattice together, and this is called the metallic bond. Okay, so this is we started talking about the electron delocalization, which means that electrons are not localized to a specific atom, but they are delocalized in the whole crystal. These individual atoms can slip over one another yet remain firmly held together by the electrostatic forces exerted by the electron. This is the reason for malleability and ductility, and for also the current flow if the metals are subjected to electric field. Okay. Metallic bonds are sometimes as strong as ionic bonds. In metallic bonds, no charge requirements, no directional requirements, and long-range effects. Okay, so this are the three different types of the chemical bonds. The first one is ionic, which is electrostatic in nature. The next one is the covalent, while the driving force is attaining the stable octet structure of the metal. And the third one is the metallic bond, which is also electrostatic in nature. How about the other types of physical bonds that exist between molecules together, the intermolecular forces? We will start talking about the dipole-dipole forces. And of course, now you know what is the dipole. Dipole. I gave example for HCl. I said the polarization in the HCl make a permanent dipole, make HCl as a permanent dipole. So this is dipole. If I have another molecule of HCl, this is another dipole. The attractions between dipole, this is the force we will talk about, dipole forces. The attraction forces between polar molecules, between polar, this is the dipole force. The next one, this is a special type of the dipole forces, which is called hydrogen bonding. When one of the atoms participating in the polar bonds is hydrogen, and the other one is highly electronegative atom, like chlorine atoms, like in HCl. So the dipole forces will be a special class. Now will be called as a hydrogen bond. Hydrogen bond. When one of the atoms participating in the attraction is hydrogen, and the other one is a highly electronegative atom like fluorine, like chlorine. So this is a special class of dipole force. The other type is the charge or ion dipole force. When you have a dipole and you have ion or a charge, so the attraction forces will be called charge dipole forces. Okay. The third one is London dispersion force. Okay. So let us talk very quickly about the first class, dipole forces. This is a molecule of iodine chloride. Okay. ICl. So the attraction forces is the between the iodine and the chlorine. What is the type of this bond? Is it intermolecular or intramolecular? Inter or intra? Inter or intra? Inter. So this is if I replace the chlorine by iodine, so this is iodine. I with I. Okay. So the bond inside the molecule is called inter or intra? Intra. Okay. Intra. So this is intramolecular forces, and these electrons are bonding electrons through bond. This is through bond. Okay. So due to the difference in the electronegativity of iodine and the chlorine, which is higher in the electronegativity, chlorine is higher because chlorine is in the second row after fluorine, chlorine, iodine, right? So fluorine is the highest electronegativity. Okay. Chlorine is next, and then iodine. So chlorine is more electronegative than iodine. So you expect to attract the electrons, the bonding electrons more. So it will acquire a sigma negative charge. And the other one will be a sigma positive charge. And this is the creation of the permanent dipole. We have a permanent dipole now. Okay. How about, so the direction of the permanent dipole from the positive to the negative. If we have another molecule of ICl, it should have the same polarization. Okay? So look at this interaction between the chlorine, which has the sigma negative, and the iodine, which has the sigma positive, but in a different molecule, in two different molecules. Okay, so this is the intermolecular force. Intermolecular force, or now we will call it dipole forces, because it originates between two dipoles, between two. So this is the dipole forces. Okay, so it is forces acting between polar molecules. This is dipole forces having permanent dipole moments. Permanent, like look at the word permanent, because we will differentiate between another type of forces when the dipole is transient, not permanent. Okay, the origin is electrostatic as well, because it operates between opposite charges. It is about 100 times weaker than the ionic attractions. So if I asked you which is stronger, the ionic bond or the lambda or the dipole forces, stronger, ionic bond of course is stronger. Okay, and it falls quickly with the distance as a function of 1 over r cube. Okay, factors affecting dipole forces, the difference in the electronegativity. Actually, when the difference is huge, the dipole moment increase and the attraction forces will increase. Okay, so you can have an idea about the electronegativity from this table. Okay, so electronegativity decrease in this way and increase among the different rows. Okay, so decrease down the group and increase over the series. Okay, the size of ions also influence the dipole moment, how close they may approach each other. Okay, so this is also another factor. The number of hydrogen bonds per atom also influence the strength of the dipole forces, or the actually when it is hydrogen bond, we will talk about the hydrogen bond, the special class. Hydrogen bonding is a special case of polar interactions occurring when hydrogen is bonded to a highly electronegative element such as oxygen or fluorine. Okay, so if this is OH in alcohol or whatever, and this is the oxygen in another molecule, the attraction forces between hydrogen and the oxygen is called the hydrogen bond. How about this bond between oxygen and hydrogen in the same molecule? Is it a hydrogen bond? Is it a hydrogen bond? The bond between oxygen and the hydrogen in the same molecule, is it a hydrogen bond? No. Why no? Because this is a chemical bond, not a physical. Hydrogen bond is a physical bond. Hydrogen bond is a physical bond. Okay, but this one is a chemical bond. Chemical bond. Okay, which is stronger? Chemical bond, of course. Okay, you should differentiate. You should appreciate this difference. Okay, so if this is a hydrogen halide, HX, where X is something like chlorine, like fluorine, like bromine, whatever. So this is a dipole moment here, and this inside here is a bonding electron. This is the bond like in HF. The green one here is bonding electrons, and this is a true chemical bond. The covalent bond is polar covalent bond, but the bond between fluorine and hydrogen here, the dotted one here, is hydrogen bond. Okay. How about the attractions between hydrogen and the carbon, and between oxygen and the carbon? Can we call this hydrogen bond? Unfortunately, we cannot consider this as hydrogen bonds, because the difference in electronegativity is not so big between carbon and hydrogen, and between carbon and oxygen. The difference is not large. I said in the definition here, this is the bond between hydrogen and a highly electronegative atom. To have a permanent dipole moment with a significant dipole moment. This is the only criteria, or the only criterion to nominate the bond as a hydrogen bond. Okay. So in ethers, for example, the oxygen is connected to carbon, not to hydrogen, and the oxygen here is connected directly to carbon, is not connected in any way to the hydrogen. Okay, directly. Okay, so we cannot consider any hydrogen bonding here. Okay, the same is applied for propane. Okay, so we cannot call this as a hydrogen. Yes, is a small difference in the electronegativity. Small difference. Yes, of course, but still higher, but not so far from the electronegativity as fluorine or as chlorine. Okay, they are still close to each other. Okay. Give reasons. The boiling points of hydrogen compounds of group 5A, 6A, and 7A decrease with the molar mass. Decrease the hydrogen, the boiling points. If you look to HF and chlorine and bromine, okay, so the boiling point decrease with the molar mass from fluorine to chlorine to bromine, from oxygen to sulfur to selenium. This way, the boiling point decrease. Why? Why the boiling point decrease with the molar mass? Okay, you should look at the attraction forces. Okay, because as we go down in the group, the electronegativity of atoms decrease. Therefore, the strength of hydrogen bonding decrease. So lower energy is required for vaporization. As you go down the group, what happened? The electronegativity decrease. As the electronegativity decrease, the bond strength as well decrease, and so you need lower amounts to evaporate or to convert to the gaseous state for the compounds. Okay. So when I ask you any question about the the properties of the liquids or the properties of gases or anything, you should go directly to the attraction forces between the physical conversion. Okay. Another question: although fluorine is more electronegative than oxygen, the boiling point of fluorine is 19.5, but for water is 100 degrees Celsius at 1 atmosphere, of course. Okay. Even fluorine is the highest electronegative atom, but its boiling point of HF is much lower than water. Okay, so now we will not talk about the difference in the electronegativity. We will talk about another parameter. How many bonds or how many hydrogen bonds each molecule can form or can participate. If you look to a single molecule of HF, it can participate from this side with fluorine in one bond, and it can participate from the other side with fluorine in another bond. So two hydrogen bonds each molecule can form. But look at water. Water can participate in 4 hydrogen bonds. So this is a unique feature for water. Water is a miracle actually for this structuring. And you know, the properties of water is different from another liquid. The density of water is much higher than the density of any other liquid, right? So water participates in 4 bonds. Everything single oxygen atom in water molecule can participate in 2 different hydrogen bonds with other 2 molecules. and the hydrogen can participate with 1, and this hydrogen with 1. So overall, we have 4 hydrogen bonds for every single water molecule. So water molecules hold together more tightly, so it requires more energy to evaporate water than HF. Okay, so the other class of bonding is the charged ion dipole, and this is actually the major attractions in the hydrations of ionic solids. If you dissolve sodium chloride in water, so the sodium ions will be surrounded with a sphere of water, and the chlorine atoms will be surrounded with sphere of this is a hydration, water of hydration. Okay, water of hydration. And you look here, this is chlorine atoms. The green one here is surrounded with water molecules this way, where the hydrogen atoms of water are directly interacting with the chlorine, which has a negative charge. So this is ion dipole attractions. Ion dipole. The same thing apply for sodium ions here. Okay, sodium ions is interacting directly with the oxygen atoms from water. So this is a class of ion dipole attractions. Okay, this attraction, this bond is a bit stronger than the dipole-dipole attraction, but still weaker than the ionic attraction. So this is about 10 to 20 times weaker than the ion-ion interaction, and it decreases with the distance as 1 over r squared. Okay, if you compare the a cation and an anion with the same charge like the potassium cation and the chlorine anion, both of them have 18 electrons. Those ions are called isoelectronic ions. Isoelectronic ions, it means that they have the same number of electrons. They have the same number of. If you compare both of them in the attraction forces here, they are isoelectronic, okay, then you will find the cation is, the cation will have the stronger attraction. The cation will have the stronger attraction because the cation is supposed to be smaller in size than the anion. The cation will be smaller in size than the anion, which means that the cation will have a higher charge density. Higher the charge, the 18 electrons are supposed to bind or to belong to the smaller size of the ion, and hence the charge density will be lower, will be higher, will be higher for the cations. So the cations will interact more strongly to dipoles than the anions. Okay. The last type of attraction forces, or the last type of the intermolecular attraction forces is called the London dispersion force. And this is a class of the van der Waals forces, the physical attraction. And this class of attraction exists actually in nonpolar molecules. In nonpolar molecules. Nonpolar molecules, it means that it doesn't have a permanent dipole moment. It has no dipole moments. So no opportunity for having ionic attractions which is permanent in nature, which is permanent in nature. So how they interact together according to the London dispersion forces? As you know, normally in the atoms, electrons moves around the nucleus in a symmetric fashion. In a symmetric, like this one here, electrons circulate around the nucleus in that shape. Okay, but this is not the case all the times. Sometimes, for any reason that you may know or you may not know, the electrons may locate together in one side and the nucleus in the other side, and this is called momentarily polarization. Momentarily or suddenly sudden polarization. To have the electrons in one side, like here, to have sigma negative charge, and the nucleus in the other side to have sigma positive charge. Okay, and this is unsymmetrical distribution. The first one was symmetric distribution. For any case, maybe some external influence may inspire this change, or even without a symmetric an external influence, the movement sometimes may deviate from the symmetric distribution. Okay, so how this momentarily polarization can affect the other molecules. Look at this here slide, this picture. This is the case of helium atom. It has 2 electrons. It's supposed to be symmetric this way, but for some reasons, electrons may come together in one end and the nucleus in the other end here to have a momentarily dipole moment. So how can this affect the other molecule? Okay, so this is one of the atom here, like this one. Okay, so this is sigma negative charge here for the electrons, and this is the sigma positive charge, the blue one, for the nucleus. This can inspire another momentarily polarization for next atoms. Okay, so it can affect the atoms in the nearest neighbor. If some atom is subjected to a momentarily polarization, it can induct another polarization for next, and this one can affect the next, and this one can affect the next. Okay, so overall we will have some sort of attraction between the atoms together, and this force is the weakest force that you can consider, that you can imagine. This is called the London dispersion force. London dispersion force is a subdivision of van der Waals. It's the major force in noble gases. It originates from the induction in nonpolar molecules. The movement of the valence electrons create transient dipoles, momentarily non-symmetric electron distribution, and this in turn induced dipole moments adjacent molecule. This transient molecule can be attracted to the transient dipole of a neighboring molecule, and the result is weak short-range attractive force. It drops off rapidly with the distance as a function of 1 over r to the power of 6. So far we have discussed all types that you can know about the attraction forces, the chemical attractions and the physical attraction. The factors affecting London dispersion forces, actually the molecular size. When the size increase, the London dispersion, the opportunity for having the London dispersion forces also increase. Okay. Also, the polarizability is the ability of the molecule to be polarized. The ability of the molecule, if you put the atoms in electric field or something like this, it may enhance the degree of polarization of the atoms. Also, the molecular shape. Look at these 2 molecules. This is normal butane, which is 2-methyl propan. 2-methyl. This is normal butane. This is normal butane. Okay, and this is 2-methyl propan. Okay, both have the same molar mass, which is 58. But look at the boiling point. The boiling point of normal butane is 0, and the boiling point of 2-methyl propan is -12, which has the highest boiling point, normal butane. So higher boiling points indicate that it has stronger attraction forces. So what is the origin of these attraction forces? Normal butane is actually a non-polar molecule. Okay, so the attraction force is London dispersion force. London between between butane molecules is London dispersion forces. But as this is a straight chain, okay, so the opportunity for having London dispersion forces is larger than the branched one here. The branched one in the 2-methyl propane. The branching may encounter the formation of the transient dipoles, encounter this. So the London dispersion forces in normal butane is stronger than in 2-methyl propane, and hence the boiling point is larger. The boiling point is large. So this is the origin in normal butane, the difference between normal butane and 2-methyl propane. Okay? And why noble gas elements have low freezing points. If you look to the freezing points here, they have very, very low freezing points. Okay? So because the freezing points, you need to cool down to have appreciated attractions between the particles together to locate in a crystal lattice to convert the liquid to in the solid state. Okay? And the attraction forces actually in the noble gas is very weak, the London dispersion forces. So you need to go down to very low temperature to be able to crystallize the atoms in the solid state crystal lattice. Okay, so this is the region. You look to these values. So how can you also compare the different values together? As you see here, as you go to down the group in the noble gas, the freezing point increase. The freezing point. So from minus 269.7 for helium, you go to Rn here is minus 71. So as you go down the group, the size of the elements increase. When the size of the element increase, the opportunity for having transient dipoles increase, and the London dispersion forces increase as well, and hence the freezing point will increase. This is the reason. Okay, so structure can also affect the properties. This is butane and this is acetone. Okay, so in butane, this is a pure hydrocarbon. It has the 58 molar mass, gram per mole. It's the same molar mass as acetone, but the structure of acetone, oxygen is connected to carbon here, which may increase the opportunity for London dispersion forces. London dispersion forces, okay? Not hydrogen bonding. You should not consider hydrogen bonding here. As I said, hydrogen bonding, it occurs when oxygen is connected directly to a highly negative electronegative atom, but here oxygen is connected to carbon. So the structure of acetone is the reason for having that great boiling point compared to butane. So the polarizability is the factor here that increased the boiling point of acetone. So if you compare the bond strengths of the whole types of bonding that we have taken, the least bonding, the least strong forces is the London dispersion forces, which exist in molecules like CH4, CCl4, fluorine, and then the dipole-dipole forces, and then the hydrogen bonding. So hydrogen bonding is stronger than the dipole-dipole attractions, and then ion dipole, and then ionic bonding. We have a question here: why is iodine a solid where Cl2 is a gas? Of course, this is at normal conditions, at room temperature and at 1 atmosphere. This is related to the different in sizes of iodine. Iodine is bigger, so the opportunity for having stronger London dispersion forces is very fine. Okay, so it can be a solid at room temperature. Compounds may involve several types of bonding. Okay, they may involve 2 categories, 3 categories, all categories, that is acceptable. Okay, for non-polar compounds, it has only the dispersion force, only the dispersion force. However, for polar compounds, it has the dispersion plus the dipole-dipole forces. And the 4 compounds capable to form hydrogen bonding, they have the same, the 3 types of physical bonding: London dispersion, dipole-dipole, hydrogen. So if I asked you, in a compound like HCl, what kind of bondings exist in HCl? It exists the dispersion, it exists the dipole-dipole, it exists the hydrogen bonding, okay? But if I asked you the major type, you will say hydrogen bonding. The major type is hydrogen bond. But if I asked you in hydrogen molecule, H2, what type of bonding in hydrogen bond? In hydrogen molecule? Only the London dispersion force, because it is a non-polar compound. Because it is a non-polar compound, okay? H2, yes, H2. So the surface tension. Let me show you this video quickly. If you look to the water in a beaker like this, okay, what's going on at the surface of the liquid here? If you look to the micro scale here, or to the nano scale even, you will see that the particles are distributed in a random state like this, okay, due to the kinetic energy of the particle. And if you look to the surface layer, you will find it not straight line, but it distributes in this abnormal shape like this one, okay? If you look to the particle inside here, it is located from all areas, from interaction forces together. They balance each other. So it is in a stable state like this one, like this one, like this one. But if you look to the one at the surface here, you will find it attracted downward and side wall, okay? But there is nothing from the top. So overall, this particles at the surface is attracted downward, is trying to shrink the size of the molecule inside here, okay? And this is encountered by the incompressibility, or the weak compressibility by the liquid. It's trying to compress the liquid, but actually the liquid is incompressible, or even has a low compressibility. So this will counter the shrinking of the size of the molecule. But if you look to the water molecules in as a drop, not in the container, you will find they assume the spherical shape, the spherical droplets. Water, when if you look to the waters coming out the biorate, for example, you will find the water molecules assuming the spherical shape, because it is trying to decrease the volume of the drop, and the volume, the least shape having the least volume, the shape which has the least volume is the drop, is the sphere, is the spherical shape. It's trying to decrease the volume, to decrease the surface tension, The incompressibility actually of the molecule can act to operate against the decrease of the surface area. So it's trying to increase the surface area. How can it increase the surface area? This can be done if the surface atoms arranged themselves in something like a skin for the liquid inside, like a skin. So particles, we need more particles to go to the surface of the water, of the surface of the liquid, to attract each other and to arrange in a form like the one that you can see here, I think. Somewhere, like this one, okay? So the interaction here, we need particles from the bulk to leave the bulk and to go to the surface to be arranged in a denser state at the surface, at a denser state. So the distance between the particles is smaller than the bulk. And to create this, we need to break the bonds in the bulk, okay? So we need to provide energy. So we require energy to increase the surface area, to act against the shrinking of the surface, okay? So this energy is basically the surface tension. This is the energy required to increase the surface area of the surface, okay? And of course, the value of the surface tension depends on the attraction forces exist in the bulk of this molecule. Let us go back to the lecture. Okay. Okay, surface tension. The unit of surface tension is joule per meter square or Newton per meter. This is the resistance of liquid to increase in its surface area. Okay, so the bulk is trying to increase the surface area, and the surface tension is trying to decrease the surface area. So the resistance of a liquid to increase its surface area, this is the surface tension. It can be measured by the amount of energy required to stretch or increase the surface area by unit area. And this explains the different types of interactions between the bulk molecule and the surface molecule, which result in the surface tension, okay? When a liquid is poured into a solid surface, it tends to bead as droplets. And this is because the surface tension is trying to decrease the surface area of the particles, and the least one is the volume or the surface area of sphere, okay? And to increase the liquid surface area, we must overcome the attraction forces between the molecules of the liquid. This required energy, since more intermolecular forces must be overcome. Liquids with relatively large intermolecular forces, such as those in polar molecules, tend to have relatively high surface tensions, okay? The capillary action is another phenomenon for the liquids, which is basically the spontaneous rising or depression of liquids in a narrow capillary tube. And this depends on the two different types of intermolecular forces, which is the cohesive forces, which is the attractions between molecules of the same type. Intermolecular force among molecules of the liquid, and the adhesive forces is the forces between liquid molecules and the container, or the different the forces between alike molecules or different molecules. So if you have water in a glass container, the intermolecular force between water molecules is called cohesive force, and the forces between water and the glass is called the adhesive force, okay? Of course, the glass surface contains many oxygen atoms that have partial negative charge that are attractive to the positive end of the polar molecule, such as water, okay? So if you look here, this is the attraction force between water and the glass tube. This is called adhesive force, and the attraction forces between water molecules themselves is called the cohesive forces, okay? So if you put a narrow tube, like a glass narrow tube, in water pool like this, you will observe the spontaneous rising of water inside the glass tube, and eventually it ends with a concave surface. This is because the ability of water to wet glass. We will say that water wet glass. Okay, wet glass, it means that it likes the interaction with the glass, because the glass, as I said, contains many oxygen containing groups. So the attraction forces between water and the glass is even stronger than the attraction force between water molecules themselves. Okay, so we'll say that water likes the interactions with glass. Okay, so basically we will observe the spontaneous rising, and this rising stops exactly when the driving force for rising, which is basically based on the surface tension, okay, exactly balance the weight of the water column. At that moment, the spontaneous rising is stopped. Okay. This tends to increase the surface area of water, which is opposed by cohesive forces that try to minimize the surface area. The other example here is the pool of mercury. Okay, we'll observe spontaneous decrease of the level of mercury inside the tube, because mercury is a nonpolar molecule. It doesn't like interaction with the glass. Okay, so it will depress this way, and it will have a convex meniscus. Okay, so this is the way of the tube. But if you look to the case of the water drops on the car glass, you will find that the water looks like beads. It appears as circles, or if the glass is covered with wax. Okay, but basically on the glass like this, it will wet the glass, because water has both strong cohesive forces and adhesive forces, but the adhesive forces is stronger than the cohesive forces. So you can observe this structure for water drops on the glass. Okay, the concave shape of the meniscus shows that the water adhesive force towards the glass are stronger than its cohesive force. This is the opposite case for mercury. Mercury will drop like this on the glass. The drop, even if you pour mercury on the floor, you will find it like beads, spheres. Okay, or in the glass like this, because actually the cohesive force in mercury is stronger than the adhesive forces between mercury and the glass. And this is the reason also for the meniscus of mercury in the glass tube. Factors affecting the surface tension is actually based on the nature of the materials and the types of intermolecular forces. As the intermolecular forces increase, the surface tension increase. Okay, and the temperature also. As temperature increase, gamma decrease, and the existence of additives in organic salts has a little effect on gamma. But organic additives as soup, alkyl acids, or esters lower the surface tension of water. And the viscosity is another property for the liquids as well. Is a measure of a liquid's resistance to flow, and the unit of viscosity is boas, and the boas equal to all these units together. Is 1 boas equal to 1 Pascal second. 1 Pascal, this is the SIU, and you need also to have an idea about the units and the convergence between them. Factors affecting viscosity, the nature of, when I say the nature, I mean the types of intermolecular forces exist. Okay, Water is highly viscous because the existence of hydrogen bonding. But look at glycerol. Every single molecule has 3 groups of hydroxyl, 3 hydroxyl group. So the amount of hydrogen bonding is huge, and that's why glycerol is much more viscous than water. Okay, the molecular mass also and the complexity affect the nature of viscosity. As the molecule becomes more complex and the molar mass increase, the opportunity for interaction or intermolecular forces increase, and the viscosity as well increase. That's why gasoline, which is a non-viscous, because it has only from 3 to 8 carbon atoms, but grace is very viscous because the carbon skeleton extends to 25 carbon atoms. Okay, so as the molecule becomes bigger and bigger, heavier and heavier, the viscosity increases. The temperature also affects the viscosity. As temperature increases, the viscosity decreases, and additives also can influence the viscosity. Addition of highly ionized salts decrease viscosity, but addition of suspended matters increase the viscosity. Okay, and so far we finished the first part about the liquid. We still have about 20 or maybe 25 minutes. Okay, so I like to go directly in the solid state. Okay, so the solid state, we have 4 different types of solid. The first one is called the ionic solids, like the crystal of sodium chloride. So the nature of bonding is ionic, and examples like sodium chloride, calcium carbonate, these types. Okay, the other type is molecular. The nature of bonding is dipole-dipole attractions or London dispersion forces. This is like the bonds in water, iodine and sucrose. So if I asked you the type of crystal lattice of water is molecular. This is a molecular solid. If I asked you, is this ionic solids in the exam, you should say no. Okay, so what is the nature of or what type of bonding in water? Is the dipole-dipole attraction or hydrogen bonding or dipole-dipole attraction. How about in the iodine? Is it the dipole-dipole in iodine? Dipole-dipole? No, because iodine is non-polar. Okay, so the nature of bonding is London dispersion. The third category is the giant molecule. It's called macromolecular. This is the nature of bonding here is covalent, and an example for this is the diamond, carbon, and silicon dioxide. These are huge molecules extend in the 2 dimensions. So the bonding here is covalent between the molecules. Okay, the last type is the metallic and is based on the delocalized covalent bonding, like the copper, sodium, and the magnesium. The first one, the ionic solids, they have high melting points. They are conductors in molten state or water solution. Okay, like sodium chloride. They are typically solids at room temperature and soluble in water, insoluble in organic solvent. These are some examples of them. They melt simple solids like sodium chloride. They melt without a change in chemical composition. So if you melt sodium chloride, the composition would be sodium chloride, NCl. But other types like polyatomic ions such as calcium carbonate, if you heat calcium carbonate, it will decompose to calcium oxide and CO2. Other types may decompose, like hydroxide decompose to metal oxide and water gas. Carbonates may decompose to metal oxide and carbon dioxide gas. hydrated salts may lose the water of crystallization. Okay, so all of these are ionic solids, and they have the same features, but they differentiate. They differ in the way they heated according to the nature of the atoms existing. The other type of solids are molecular solids, and these are solids at room temperature, have strong intermolecular forces. They include nonpolar substances of high molecular mass, such as iodine, naphthalene, or ice, or urea. All these are examples for molecular solids. So I may ask you in the exam, I give you some properties for some material. As I said here, a solid material at room temperature. So you may think about ionic solids or molecular solids, okay? And then I say they have strong intermolecular forces, and then I may say they include, they have, for example, London dispersion forces between the molecules together. Then you should go directly to the molecular solids, okay? As the bonding is London dispersion forces, okay? The third type is macromolecular solids, atoms held together in a two-dimensional network like this of electron pair. This one example for diamond, for example, and the other one for silicon dioxide. Okay, these examples for macromolecular solids. The last one is metallic solids. They are conductors of electricity and the heat, ductile, malleable. Their surface area are good reflectors of light. And these examples, sodium and magnesium. Okay. Lattice energy of magnesium is greater than that of sodium, of course, because every single ion has two delocalized electrons connecting the atoms together. Okay, structure and bonding in metals. Okay, so we'll spend some time talking about the backing of elements in metals. Okay. Metals are characterized by high thermal and electrical conductivity and ductility, malleability, because the non-directional covalent bonding in metallic crystal. Metallic crystal can be pictured as containing spherical atoms. Usually we consider the spherical particles, spherical, because it has the least surface area, as I said, okay? And the atoms is trying to decrease the surface area to decrease the surface tension, okay? A metallic can be pictured as containing all spherical atoms. They back together uniformly and most efficiently, using the available space and bonded to each other in all directions equally, which is called closest backing. If you want to connect atoms together, we will see different modes of backing. And for every mood, we should consider the backing efficiency. Which one has the highest backing efficiency? Okay, so atoms is trying, when held together, to have the best backing, okay? Look at this model. If atoms is connected, are connected together in this way, okay? Even if a bond exists between these atoms, okay? Is this better or is this better to touch each other? Which one will have the higher efficiency of backing efficiency? This one, of course. The spaces between the atoms is least, right? Okay. So look at this one. This is called square close backing. Okay. And the backing efficiency is almost 52.48. Okay. of available space. But look at this. If you slide the rows a little for every row, you will have a very small triangle voids between the particles together, okay? And this is called the closest backing, closest backing. So the backing efficiency of this type can achieve something about 60.4 of the available space. Very small voids exist in this backing, okay? So when we will talk about closest backing, so we will consider backing in the first layer like this. The second row is a bit slided, is a bit shifted from the first row, and the third row as well the same, okay? Like, and you go in this way, okay? So this is called the closest backing, okay? So the sphere are backed in layers in which each sphere is surrounded. So in the backing this way, even if you go to this slide here, okay? How many atoms attaching the atom in the middle here? How many atoms around here attaching? You may count here. How many atoms? 6 atoms attaching the one in the middle, right? This is the same here. This is the middle one, is the red one, and 6 atoms are attaching. So we will say in the same row, 6 atoms are surrounding the atom for each atom. 6 atoms surround each, they touch the atom in the middle directly. They touch the atom in the middle directly, okay? So how about if you want to build another row of atoms, okay? So in the voids that I described in the last slide, the way we can build up the next row, the above one, okay? We can put atoms in the voids, in the triangle voids. So for every space here, we can put another atom. But if you put the atom here, you cannot put it here. The next one you cannot put here. You can put here. So we will put in one void and leave the next one. Put here and leave this one. Put here and leave this one. So how many atoms can be touching the atom from above? 3 atoms, okay? Like this one, okay? And from the bottom, also 3 atoms can touch. So how many overall, how many atoms can touch this atom, or how many atoms can surround this atom, the red one? 6 in the same layer, 6 in the same layer, okay? And 3 above and 3 below. So overall, we will have 12 atoms. 12 atoms. This is the coordination number. This is the coordination number, or 12 equivalent neighbors, okay? But we have 2 different cases for arrangement, okay? Okay. Okay, this is the first layer. We build the first layer here. They are in the first layer, okay? You can expand this layer as you wish in the 2 dimension. Okay, 2 dimension. How about the 3rd dimension? You can also extend this unit or this structure in the 3rd dimension, okay? How can you extend in the 3rd dimension? You put in the voids, this void, you locate one from above. And how about the next layer, the other layer from the other side? You can put one also in the same void from the other side, or you can put it here. But if you put anyone in this void, you cannot put another one in the next void here, because space will not be available for you, okay? So you can put one here, and one here, okay? from this layer. How about the other layer? You can put them directly in the same manner like this layer, or you can change and put it in the other voids. But if you put here, you can put here, and you leave also the 3-1. So we have two different structuring. Okay, so the layers will be located as A, P, A, which means that the layer in the third layer is exactly above the layer, above the atoms in the first layer. Okay, so you put them in the same voids, in the first layer and in the third layer. But and this structuring is actually called hexagonal closest backing. Okay, so if you extend the crystal in the 3 dimensions, you will see this is the atom in the second layer. This is in this triangle, and as I said, if you put in this the atom in this triangle, you cannot put here. Okay, so you put in the other one and go this way. How about the third layer? The third layer can be located exactly above. This is the first layer. This is the first layer from the other side. Okay, so the second one is plotted here directly above. This is APA. Okay, so this is the yellow, empty yellow. Okay, so this is the third layer. The third layer comes directly above this layer. Okay, so this is first layer, this is second layer. How about the third layer? The third layer comes directly above this, above, right? Or the blue one. Okay, the blue one comes directly above the other blue layer here. So the arrangement is basically in that type is called APA, EPA. And if you extend the crystal lattice in the 3 dimensions, you will find this. If you turn it to angle of 45 degree, you will observe the hexagonal crystal lattice like this. This is the unit cell of the hexagonal closed backing, the unit cell. And the unit cell is the smallest repetitive structure of the material, the smallest repetitive structure. If you extend the unit cell in the 3 dimensions, you will get the whole crystal lattice. Okay, so this is called hexagonal closed backing, or we can nominate it as HCB. This is HCB. The other type of arrangement, if you put the atom in the third layer in another void, in the other voids. Okay, so you switch the other voids, so you end up to this structure. Okay, so we have 3 different arrangements: ABC, ABC, ABC. Okay, so if you extend this in the 3 dimensions, you will end up with the cubic crystal lattice, cubic or face-centered crystal lattice, face-centered FCC unit cell or cubic closed back CCB. Both are the same. And many elements crystallize in this structure, and others in the hexagonal crystal structure. Okay. Of course, I will show you a video that simplify this structuring. Okay, but let us make it at the end of the lecture. Okay, so the unit cell actually is the smallest group of atoms which has the overall symmetry of the crystal, and from which the entire lattice can be built by repeating in 3 dimensions. For face-centered cubic, this is the smallest repeating structure, which is CCB or face-centered cubic. Okay, so by rotation here you can find the structure is like the one here. So 8 atoms located at the edge of the cube, and 6 atoms are located at the faces of the cube. 6 atoms are located at the fix at the faces of the tube. We have three different types of the cubic crystals here. One is the simple cubic, where 8 atoms are located at the edge. The body center, the cubic, 8 atoms are located at the edge, at the corner of the cubes, but 1 plus 1 inside. And for the face center, do you take a course for symmetry or like this in geology? Geology, the first semester? Not all of you. Some of you. Okay, okay. Okay, this is the face center of the cubic. The face center of the cubic, we have also 8 atoms are located at the corner, and 6 atoms are located at the face of the cube. How many faces are existing in a cube? How many faces? A cube? 8 or 6? 6 faces. What did you get the extra 2? 6 faces. Okay, and we have how many edges? How many edges between faces? How many edges? 8? Okay. 8 or 12? 8 or 12? 8 for each side here, okay? For each face has 8 edge, right? And the other side has also I'm saying 4 for each face, and for the other face we have also 4, and we have the other edges here. So basic a total of 12 edges. Okay. Okay. So the net number of spheres in face center of the cubic. Okay. Look at this atom here. This one of the atoms at the corner of a cube. Actually, these atoms do not participate in a single cube, but it participates in 8 cubes. How is that? Okay, because as I said, the unit cell is the least repeating structure with the symmetry of the crystal, which when expand, it gives the whole crystal. Okay, so this atom is located in the edge of this cube, but it also interacts with 4 other cubes here in the same layer, and interacts with another 4 cubes in another layer. Look at this particle here. Those are 8 cubes. The atom participates in the 8 cubes, right? Okay. So we have here atom. We have also here atom, but it has other cubes in this side. Okay. So every single atom in the edge of in the corner of the cube participate in 8 cubes. So basically, the contribution of this atom for a single unit cell is basically 1/8. 1/8 of atom. 1/8 of an atom. Okay. How about the other faces? The atoms at the faces. Every single face, like this one here, okay? This is a face. If I have an atom at the face here, it can interact with another cube. Only one cube. And if we have an atom from the other side here, it interacts also with one cube. So atoms existing at the face participate actually by half to every single unit cell. Participate by half for every single unit cell. So for face center of the cubic, we actually have 8 atoms at the 8 corners. but every single atom contribute with 1/8 to a single unit cell. So overall, the 8 atoms contribute together by one atom, by only one atom. This is 8 times 1/8, but also at the faces, we have 6 atoms at the faces, but every single atom at the face contribute by half an atom, So overall, for face-centered cubic, we have 4 atoms. We have four atoms. Okay, this is for face-centered cubic. How about and this table summarizes the contribution of the atoms here. For cubic corner, we have 8 atoms, but everyone contribute by 1/8. For the edge, we have 4 atoms, but everyone contribute by if we have an atom at the edge, so we will have 4. Everyone will contribute by 1/4. Atoms at the face, the number of sharing atom is 2 for the face, so everyone will contribute by half. For the bulk, every single atom in the bulk contributes by 1 atom completely for every unit cell. So in the cubic unit cell, the simple cubic, we have 8 atoms at the corners. So overall, we will have 8 times 1/8 equal to 1. And for the BCC, body-centered cubic, we have 8 in the corners, but 1 in the middle. So overall, we will have 8 times 1/8 plus 1 times 1. This equal to 2. Okay, I will stop here and continue in the next lecture about the density of loose packing. And I will send you, inshallah, the video that explain this structuring probably better, inshallah. I want you to see the video to be able to continue next lecture in this part, inshallah. I will see you next lecture, inshallah. Okay, let me just thank you very much.